Hi there. Thank you for clicking on this video. This video is going to start a 2-lesson sequence on complex numbers, and we're going to start with just an introduction to imaginary numbers. Now, I say that right at the outset because if you've clicked on this video looking for something very specific about complex numbers and you don't see it in this video, it is likely it is in the next video. It's in the second video. It's just that there's a little bit to go through, and it's often very, very new to students, so it's not the kind of topic we want to just zoom right through. Please like this video if you find it helpful, subscribe for more math content, and please check out the other videos on the channel, including the practice set for this lesson and the accompanying second lesson on complex numbers. Now, what is all this about real numbers? You've probably noticed that we talk about real numbers and often define them as the numbers on the number line. So you've got your number line, we've got 0 in the middle of the number line, we've got positive numbers going off to the right, negative numbers going to the left, and we say real numbers are any of the numbers on that number line. So positives, negatives, decimals, fractions, 0, all on the number line, all real. But this implies the existence of some numbers that are not real. Otherwise, we would just say the domain of a quadratic is all numbers. But we don't say all numbers, we say all real numbers, which means somewhere out there, there are numbers that are not real and do not exist on the number line. In this lesson, we finally get to see what those numbers are. Now, I mentioned earlier imaginary numbers, that is what we're introducing today. And just for full disclosure, because I remember studying this when I was in high school and being upset about it, being very upset that my teacher was wasting my time on numbers that were not real. That this is, I live in a real world that does real things, and I don't mind learning math, but I at least want the math I learned to be like real math. And my mom, who was a math teacher, she didn't sympathize with me. She was just like, you need to learn this anyway. Now, fast forward about 4 years after that, when I was in college and studying engineering, I actually used these numbers. So I didn't think that they were useful for anything. I really, really, truly thought they were a waste of time. And then lo and behold, it turns out they actually do things in the real world, even though the numbers themselves are not real. All right, so without further ado, we're going to start with a discussion of I. Now, right here, this is a lowercase I. When I typed this, I did put it in italics, but you will often see people handwrite it like that, sometimes like that. It's going to have a little bit of like a curve to it. I've seen like a cursive I used. Typically, we don't just use a printed I, although when we're typing, we do, because it is too much of a pain to go back and just like italicize or change the font for like one character. And it's one character that appears over and over again. So when you're looking at it in typewriting, it'll just look like a lowercase I. Now, fun fact, I did mention that when I was studying engineering in school, we used these. In electrical engineering, we used a J, okay, instead of an I, because I was already being used. So we ended up using a J. So what is I? Okay, I is the imaginary number. So if somebody says, what are you studying with? The imaginary number. And maybe it's a little unfortunate that we've called it an imaginary number instead of maybe the alternate number or the like really cool, not on the number line number. Just the very fact that we use the word imaginary makes it seem kind of like a fluffy thing to study, but anyway, that's I. It's the imaginary number. You can tell there I just typed it as a lowercase I. Now, here's what it is. We know that there's no real number that's squared that can give us a negative, and I got the reasoning there. If you have a positive number and you square it, meaning you multiply it by itself, you will get a positive number. So, if I pick 5 and I square it, that is 5 times 5, which gives me like positive 25. And it's also true that if you take a negative number and you square it, you will get a positive. So if I have -5 and I square it, that's -5 times a -5, and a negative times a negative is a positive. And then the only other option we have is 0. And if I square 0, I get 0 times 0, which is 0. And you notice none of those are negative, okay? And that accounts for everything on that number line, okay? So there's my real number line. I've got positives. They won't square to give me a negative. I've got negatives. They don't square to give me a negative. And the only one that doesn't fit either category is 0, and that doesn't give me a negative either. So no real number. There is nothing on that number line anywhere that when you square it can give you a negative. Now let's suppose there is some kind of new number that when we square it, we will get a negative. That's what I is, okay? And we needed a symbol for this like hypothetical new number that when we square that number, we actually do get a negative number. And it can't be anything on the number line because it would violate the rules we know about multiplying numbers. So it's got to be some other number that we don't see on that number line. Now, there are two ways we handle the definition. This is one definition. It's just written two ways. So you can see the definition written as squaring. So I squared is equal to -1. Okay, so that's first way that we think of it. The second way is as a square root. And if you picture that first equation there, I squared is -1, and you just take the square root of both sides, well, the square root of I squared would be I, and then I must be equal to the square root of -1. Okay, and so it's really the same definition. It's just sometimes we'll write it with the squaring and sometimes we'll write it with the square root. Okay, both of those definitions come in handy and useful at times. Okay, now what this does, it's going to open up some possibilities with some things that we've already studied. So one of the things this does is it allows us to simplify square roots of negatives. Up until this point, up until the point when you study imaginary numbers, if you get a negative under a square root, you have to stop whatever problem you're in and you say no real answers. And there's that word real coming up again, like no real answers. Well, maybe there's some other kind of answer. So how does this work? So if you have the square root of -4, and what I usually have my students do, and you can pause the video and do this, is grab a calculator and type in the square root of -4. Just see what your calculator does. Unless you've got a calculator that does complex numbers and somebody has put it in the mode for doing it, it will typically say something like non-real answer. It will error, it'll display an E, it's not going to give you a number, okay? It'll error somehow. So here's how we can reason this out. We know that -4 is equal to 4 times -1. So essentially what I did there was I just factored the -4 and I factored it to pull that -1 out, okay? We know that this is true. The square root of -1 is equal to I. So I'm going to kind of pull that -1 out. And then our rules for dealing with radicals say that this is the square root of 4 times the square root of -1. Well, the square root of 4 is 2, and now I actually know what this is. I know the square root of -1 is I, so the square root of -4 is 2I. Okay, it's not 2, it's not -2, it's 2I. And we don't usually do all those steps, and I have had students get confused at times thinking like it was very important that you showed all of them. But if you would like to do something like this, like the square root of -9 is equal to the square root of 9 times the square root of -1. So the square root of 9 is 3 and the square root of -1 is I. You can do that. I've had students do this. Try that again. Do this when they do the 9 times -1 and then they do the square rooting from there. Or you can show like both steps, like the splitting of the radicand and the splitting of the radicals in separate steps. It's really up to you. Okay, and then over here we've got what the square root of negative 24. And so that would be the square root of 24 times negative 1. Now, 24 is not a perfect square, so we've got to think, what is a perfect square factor of 24? That would be 4. Okay, so we have 4 times 6 times negative 1. So now we have like 3 radicals in here. Okay, square root of 4 is 2. Square root of 6, we're like stuck with that. We're not super happy about that. Square root of negative 1 is I. And then typically what we'll do is we'll just kind of like move that over there. That's all multiplication. That way we don't have stuff sitting on both sides of the square root. Okay. And typically we do move stuff around to the front for clarity in our notation. And I'll just kind of show you what we mean by that, the clarity in the notation. If you do something like this, if you were to do the square root of 2i, like I'm not 100% sure whether that I is out of the square root or inside the square root. Like it just gets a little bit messy. So if it's not under the square root, we do the multiplication on the left rather than on the right. Okay, so that's one of the things that the imaginary number will allow us to do. Basically, we simplify the square root as normal, and we just remember the I will be in there as a result of the negative. Now, I don't teach it that way. I would never tell you, hey, if you see the square root of a negative, just put an I in your answer. You want to know why there's an I in your answer, and the I comes from the negative 1. So the times negative 1 is where that I is generating from. But yeah, pretty much like you take the square root of 4, the square root of 9, and you'll have an I. But the I is coming from the negative. Now, I also has an interesting modular behavior, and this is one of those topics that sometimes I will skip. It's not mission critical. It is actually it's a weird thing that shows up in a couple of isolated places, but it is interesting. So I want you to consider this question. If today is Friday, which it is the day I'm recording this. So if today is Friday, what day of the week will it be 497 days from today? And I will often posit a question like that to my classes and just say, okay, I want you to think about it. And so you kind of, I mean, you can pause the video and just kind of think about that, like 497 days from today, what day would it be? And we kind of go through what we can do is like grab a calendar and count out 497 days. That would work. But what most students start to realize is that you are going to repeat the days of the week every 7 days. And so what a better way to do that is to figure out like how many groups of 7 you have in there, like how many weeks are in there, and then like subtract all of those out essentially, and then figure out what's left over. So this problem involves something called modular arithmetic. It was something that I studied when I took a course in grad school, actually called number theory, but you could take it as an undergrad as well, in which the elements of a sequence repeat. Okay. In the case of the days of the week, we call that mod 7. We say the mod is 7, or we're modulating it. By 7, it just means we go like Sunday through Saturday, or if you're not in the United States, you might go like Monday through Sunday. It's kind of depending on what you consider the first day of the week, and then you repeat them. So by the time you get to day 8 is actually the same as day 1. Like they are both like Fridays or Mondays or whatever it might be. So our behavior with I actually does something similar. So we're going to kind of hash this out. So I to the first power is just I. Okay. I squared, that's part of our definition. I squared is -1. Now it gets a little bit weird. I'm going to move off to the side here to do my scratch work so that I don't muddy this area up over here. All right. So I to the third power, that would be I squared times another I. But I squared is -1. So it's -1 times I, and -1 times I is -I. Then we come to I to the fourth. Well, I to the fourth is I squared times I squared. You could get there other ways too, but I squared is -1. So -1 times -1 is +1. I to the fifth. Well, I to the fifth would be I to the fourth times one more I. But I to the fourth, remember, is 1. So that is just 1 times I. And notice that we're back where we started. So by the time I get to I to the fifth, I'm actually back at where I to the first was, which means that we are going to end up in like this pattern where we keep like putting an I in. So I to the sixth would be I to the fifth times 1 more I. But it is essentially, well, we'll go I to the fifth is I. So it's I times I, which is I squared, which we know is -1. And so we could keep going with this, but what you want to notice is that we have this pattern of 4. I, -1, -I, I, -1, -I, 1. I, -1, -I, 1. And so it has this what's called mod 4. So it modulates and it's going to repeat every 4. So unlike other things that you might keep multiplying in over and over and over again, and you end up with bigger and bigger and bigger numbers or smaller and smaller numbers, it depends on what you're doing. I doesn't do that. I just like keeps this cycle through these like 4 things. Is this an incredibly useful fact? Probably not. I have not in my math career needed to know this, but it is kind of an interesting thing. Like, oh, this is a neat little way that it behaves. Okay. Now, so that brings us to this kind of question here. And you can debate, whether this is useful or not, but this is called simplifying higher powers of I. And it's just, we take that I to some big number and we want to see what is that equal to. Now, remember that I to the first was I squared was -1, I to the third was -I, and I to the fourth was 1. So could we keep counting all the way to I to the 243? Sure, but neither you nor I have enough time for that. A better way is to figure out how many chunks of 4 do I have in there, and what is left over. And so one of the best ways to do this, this is my opinion, I've seen other people do it other ways, is to take the 243 and divide it by 4. So we go in, 4 goes into 24 6 times, bring down the 3, 4 goes into 3, it doesn't. And so I've got 3 left over. I've seen students do this other ways too, though. They've done like 60 times 4 is 240, and then done the 243 minus 240 to get the 3, which is essentially what we do with long division. And the important part there is that it is like left over, like you've got 3 left over. So essentially, I to the 243 is the same as I to the third, which means it's -I. If you don't get any remainder at all, that means it's divisible by 4. It is divisible by 4, okay, and it would land you at the 1. Sometimes I've done that with like I to the 0, like so there's 0 remainder, but if you haven't really talked about 0 exponents, that's not the best way to go with that. Now, interesting behavior. Maybe it's useful somewhere. Just because I haven't seen it doesn't mean it's not there. Now, the last thing I wanted to look at is this does allow us to solve all quadratics. So up until this point, we would not have a solution for this problem over here on the right. Something squared plus 4 would give us 0. Well, that can't be, because if I square it, it's going to be positive or maybe 0, and then I add something to it, it's not going to go back to 0. But now we have some tools to be able to do that. So I'm going to subtract 4 from both sides. X squared is equal to 4. Now I can square root both sides. Remember, when we do that, we do need the plus or minus. The square root of x squared is x, and I end up with plus or minus the square root of -4, which we did earlier in this lesson is 2i. So now we know that the solution for that quadratic is plus and minus 2i. There's 2 answers, positive 2i and negative 2i. Now, just to compare that to the graph, if you look at the graph here, we could not solve this graphically. So if we tried to solve this graphically by setting it equal to y and looking for the x-intercepts, notice that there are no x-intercepts. And so that is our tip off that the solutions to this will be complex. If they were real, they would be crossing that X number line at whatever those real answers are. So no x-intercepts means there is no real solution, but there are two imaginary ones. Okay, so that's a wrap. Please don't forget to like and subscribe if this lesson was helpful to you. Drop a comment or ask a question below, and check out the practice set and the other videos we have on the channel. And if this did not cover the thing that you were looking for with complex numbers, the next video is going to cover how to operate with complex numbers and go through rationalizing the denominator, all that fun stuff. So I hope to see you in a future video.